Welcome to the lecture on cyclic codes. So, in cyclic codes, we will first try to give a polynomial representation of codes. So, you have a code C0, C1 up to n minus 1. So we can alternatively represent a code as a coefficient of a polynomial. Suppose I define a polynomial c of x as the first term is constant c0 plus c1x plus c2x square plus cn minus 1 x n minus 1. Okay, so it means that suppose if this is 1 0, suppose if your code is 1 0 1 0 1 0 1 1, so it means c0 will be 1, this will be 0, this term will be 1. Okay, so there will be such 7 terms, but only 4 will be positive 1, others will be 0. X is any dummy variable here, we call it indeterminate. Okay, it's just the main thing is the coefficients. Okay, we will see the power of this polynomial very soon. Now, if you look at a binary source which emits these digits, okay, so suppose you have this c0, c1 up to cn minus 1, right? So as time moves you get one digit. So first you may take out c0, right, then c1, okay, and then finally cn minus 1. So you can see that the degree of polynomial represents actually shift in time. Now what exactly it means is that if you want a shift, if you want to shift this code bits to right side one bit, so what you should do, just multiply x by c of x. Okay, so when you will multiply this x by c of x, it is equivalent to shifting, right? So you get x c of x as c0 x plus c1 x square plus c2 x cube plus cn minus 2 x n minus 1, or plus cn minus 1 xn. But the only issue with this, so you can see the shifting, right? So this c0 now has a degree, c0 has here x has degree 1, so it means that c0 has moved to the place of c1. C1 is now multiplied with degree x square, it means it has moved 1, but there is this term x to the power n, right? And actually we want to represent by polynomial something called cyclic shift. See, what should cyclic shift do? Cyclic shift should do, suppose this is the original code, if I do one shift, cyclic shift, so I should get here cn minus 1, c0, and then cn minus 2. If I take one more cyclic shift, I should get cn minus 2, cn minus 1, c0 up to cn minus 3, right? This is what we want. Now, how to get that? We will not go into the polynomial theory this time. We will directly use some of the results there and get as much intuition as possible. First of all, it is clear that shifting will be realized by multiplying appropriate degree of x with the code polynomial, but we need to do something more. So as a first step, suppose if I want I shifts, okay, so what I will do is I will multiply x to the power I with the code polynomial c of x. I will obtain c0 x to the power I plus c1 x to the power I plus 1 plus. So there will be some ith term that will be denoted by cn minus I minus 1 x to the power n minus 1 plus finally Cn minus 1 x to the power n plus I minus 1. Now I will take x to the power n as common, but before that we will write some of the terms in more detail. So let's write it again. C naught x to the power I plus C1 x to the power I plus 1. Then we have C of n minus I minus 1 x to the power n minus 1. What will be the next term? C of n minus I x to the power n plus C of n minus I plus 1 x to the power n plus 1 dot dot dot, then C of n minus 1 x to the power n plus I minus 1. Okay, now I will take x to the power n common from these terms. Let's see what we will get. This is what we get. Just verify it. Okay, I have taken x to the power n common, and then the other terms. Now after this I will do one manipulation. Okay, so to do that manipulation I will note, see these coefficients C0, C1, C2, they are all binary, right? So you take any two coefficient, suppose C0, if I add C0 to it, it will be 0 because it is either 1 or 0. 1 plus 1 is 0, 0 plus 0 is 0, of course. Similarly, if I take C of n minus I, if I add C of n minus I to it, it will be also 0. C of n minus I minus 1 plus C of n minus I minus 1, it will be also 0. Noting that, what I will do is, look at here, I will write here again C of n minus I, again add C of n minus I. So this together is 0. I can do this. Similarly, I will write here C of n minus I plus 1 plus C of n minus I plus 1 times x. Anyway, this is 0. So it is as if I am writing 0. Plus Cn minus 1 plus Cn minus 1 times x to the power I minus 1. And then there are other previous terms, C0 x to the power I plus C1 x to the power I plus 1 plus Cn minus I plus Cn minus I minus 1 x to the power n minus 1, right? So no issues with it. This term, these are all actually 0. Now I will do one thing. So x to the power n. So let me first of all represent, let's define the polynomial inside the x to the power n on the right hand side as q of x. That is q of x, let it be C of n minus I plus C of n minus I plus 1 x plus C of n minus 1 x to the power I minus 1. Now with this representation, it becomes x to the power n q of x. Okay, now I will write the second term, this term. Okay, I will now write it in this way. First of all, I will write the first term of each bracket, that is, I will write C of n minus I plus C of n minus I plus 1 x plus C of n minus 1 x to the power I minus 1, right? Then I will write it again, C of n minus I plus 1 x plus, first I will write C of n minus I plus C of n minus I plus 1 x C of n minus 1 x to the power I minus 1, and then the other terms plus C0 x to the power I plus C1 x to the power I plus 1 plus cn minus I minus 1 x to the power n minus 1. Now you note this also is q of x, right? So it becomes x to the power n q of x plus q of x. Now this polynomial, I will give it a notation of c bracket I of x, and hence it becomes x to the power n plus 1 times q of x plus ci of x, where what is this ci of x? It is this polynomial cn minus I plus cn minus I plus 1 x plus cn minus 1 x to the power I minus 1 plus c naught x to the power I plus cn minus I minus 1 x to the power n minus 1. Now what is this ci of x polynomial? Let's look at it. Let's see a code word c with bits c naught, c1 up to cn minus 1. Its code word is c of x, c naught plus c1x plus cn minus 1 x to the power n minus 1. Okay. Now let's do I times cyclic shifting. I times or ith cyclic shift of c. This code word. See, when you will do the cyclic shift for once, you will get cn minus 1, c0, cn minus 2, right? Second cyclic shift cn minus 2, cn minus 1, c0, cn minus 3. What will be the ith term? That will be cn minus I, right? Then cn minus I plus 1 dot dot dot. Then there will be somewhere in between the terms cn minus 1, c0. Then there will be the last term cn minus I minus 1, right? This is the ith cyclic shift to this code. And what is the polynomial for it? That is exactly ci of x. If you write polynomial for it, you will write first degree 0 degree term will be c of n minus I, then c of n minus I plus 1. See, this is not given in the book this much detail, so note it down properly. X plus c of n minus I plus 2x squares dot 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 plus c of n minus 1, c of n minus 1 of x to the power n minus 1, right, plus, and then finally c of n minus I minus 1 this will be x to the power I n minus 1. Oh, so this will be, sorry, this will be I minus 1. I'm sorry for this. It will be I minus 1. Yeah. Okay. So it means that when you multiply a code polynomial with x to the power I, you can write it as q of x times x to the power n plus 1 plus ci of x. It has a very nice interpretation in the theory of polynomials. What is that interpretation? If you divide x to the power I c of x, if you divide it by x to the power n plus 1, okay, suppose this is your x to the power I c of x, this is your x to the power n plus 1. So what will be the remainder of this? Okay, that remainder will be ci of x. Okay, see, look at the basic mathematical expression. Suppose you have 10 divided by 3. So 10 divided by 3 is this is 9, 1. So you can write 10 is equal to 3 into 3 plus 1, right? So this will be actually your q of x. So this will be your q of x, and this will be the remainder, right? So to get a cyclic polynomial for a cyclic code out of a code polynomial, divide the code polynomial by x to the power n plus 1, then the remainder which you will get is a cyclic code. Okay, so this is very important property. And this type of multiplication, suppose we then write ci of x, this cyclic code is equal to x to the power I c of x, we write it modulo x to the power n plus 1. Okay, for any I cyclic shifts. Okay, and this polynomial has very important role to play in a cyclic code, so we will see that very important role. Now let's first come to the how to generate the codes. So in linear codes you had a generator matrix G. So in cyclic linear codes we have generator polynomial. Generator polynomial. Before I discuss generator polynomial, let's first of all take a message. So if you remember last time we represented message vector m, which had these components m0, m1, mk minus 1. This is a k bit message, right? So corresponding to this message here we will have message polynomial, right? Message polynomial that will be represented as m of x is equal to m0 plus m1x plus m2x square plus mk minus 1 x to the power k minus 1. Now you recall from previous discussion that your code had two parts. One was the parity bits b and the message bits, right? Now parity bits are n minus k bits, so suppose b0, b1 up to b of n minus k minus 1. So corresponding to parity bits we will have parity polynomial b0 plus b1x plus bn minus k minus 1 x to the power n minus k minus 1. Okay, now how to represent a code word, right? So that is very important. See, you have a code C with a code polynomial of degree n, n minus 1. Okay, so c0 plus c1x plus cn minus 1 x to the power n minus 1. So this degree is n minus 1. Now if you look at the message bits, okay, so definitely it has a degree k minus 1, and if you concatenate parity bits to it directly, so what is the degree of this? Its degree is n minus k minus 1. Okay, and what you want is so the first c0, that is actually b0, right? Because the first part of code we are taking as parity bits. So it means when I had write polynomial for this, I will write b of x. But what is the last term in parity polynomial? The last degree is x to the power n minus k minus 1. After this, the next degree that should come should be n minus k, right? But if you write directly the message bit, you have m0. But it should be actually m0 times x to the power n minus k, right? Similarly, the last degree for message is x to the power k minus 1, whereas last degree should be x to the power n minus 1. So what is the solution? So to represent code polynomial in terms of message and parity polynomial, you multiply message by x to the power n minus k. Now you cross check you will see x to the power n minus k times message will become m naught x to the power n minus k plus m1 x to the power n minus k plus 1, and last term will be m k minus 1 x to the power n minus 1. This is what we want. So this is the proper way to write a code in terms of parity and message polynomial. Now see what is given to you. Message, you need to find the parity polynomial. If you get parity polynomial, you can get the code word. You can get the code polynomial, and hence the code word, cyclic code. Now to get that, we will first define a generator polynomial. So if you remember, generator matrix was n cross k. Now generator polynomial has a degree n minus k. Okay, actually the logic is that you should get code word by multiplying some polynomial with generator polynomial, right? This polynomial should have same number of bits as message bits, hence it should have degree k minus 1, right? So if you take generator matrix and code has a degree n minus 1, for code to have degree n minus 1 and you multiply it with some polynomial which is of the same length as that of message bits, that degree is k minus 1. So the degree of g of x should be n minus k. Just remember this as a fact if you don't understand this point. Degree of g of x should be n minus k. So I can write g of x in general. So there is a constant term which is always 1, and since it is degrees n minus k, so there is a term n minus k with coefficient 1 always. In between there will be terms of other degree x to the power I. Their coefficient will be g of I for I equal to 1 to n minus k minus 1. So gi may be 0 or 1, okay, depending upon the structure of the code. So this is your generator polynomial, and we will generate the code as c of x is equal to a of x g of x. Okay, a of x is some polynomial with degree k minus 1. Okay, and we are seeking the systematic code. That is why we have written code word as this, because in this cyclic code the m of x is retained as it is. It is not changed. Code word, one of the part of the code word is message bits also. So now we have written code word in two ways. One is ax times generator matrix. Generator matrix is given to you, mind that, okay? And our target is actually to find the b of x. And also we can write it as b of x plus x to the power n minus k m of x, right? Now if I equate this equation 1 and 2, okay, so I get a of x g of x is equal to b of x plus x to the power n minus k m of x, right? Now if I divide both sides by g of x, I will get a of x is equal to b of x by g of x plus x to the power n minus k m of x by g of x. Since we are doing modulo 2 operation XOR, so plus minus is same here, so I can shift this x to the power n minus k m of x by g of x here and write it is equal to a of x plus b of x by g of x. Now what does it mean? It means that if you divide x to the power n minus k m of x by g of x, right, then if you see the the way of division, then b of x, whatever you will get here, b of x will be the remainder of it. Okay, so now here is the way you know, to generate NK cyclic code, what is given to you? You are given the generator matrix G of X. Step number 1. So pre-multiply M of X by X to the power n minus K. Step 2. Divide X to the power n minus K M of X by generator polynomial, and what will be the remainder? That will be the parity polynomial. Okay, B of X. Step 3. Write C of X is equal to B of X plus X to the power n minus K M of X. This will be the required code. Okay, very simple generation. We will do one example that will make it more clear. Now there is a task of decoding. Okay, now when you will transmit the code word, then you will receive some binary vector, and then you have to decode it. If you remember, with linear codes we were having parity check matrix. In cyclic codes, equivalently, we have something called parity check polynomial. See, the cyclic codes will become easy. The theory initially seems to be difficult, but examples are very simple, and while doing examples, we will get a more understanding of what we have done till now. It's not so difficult. This is the easiest part in digital communication, I think. Okay, and the degree of this polynomial is k. This will become more clear why it is k with examples. We will not go into proof way. We call it parity check polynomial. Since its degree is k, so there has to be a constant term, and there has to be a degree k term. There will be coefficient 1. In between, there will be terms which may be 0 or 1 depending upon hi is 0 or 1. This is your parity check polynomial. Okay. So I state here a fact without proof. I am saying without proof. It needs a proof from polynomial theory. The fact is, generator polynomial has degree n minus k times parity check polynomial has degree k. The resulting polynomial is actually equal to x to the power n plus 1. It has degree n. So I told you initially that x to the power n plus 1 has very important role to play in the whole theory of cyclic codes. This is one of the reasons. The parity check, the generator polynomial and parity check polynomial will have such a structure that when you will multiply them, you will always get x to the power n plus 1. Right? So if you have, suppose, 7-4 code with n is equal to 7, right? When you will multiply gx hx, you will get x to the power 7 plus 1 for sure. Then only it is cyclic code. Okay, I will not prove it. It has a proof. We will not prove it. We will take it as a fact. If this fact is true, then it means definitely that if you take g of x and h of x, if you divide them by x to the power n plus 1, the remainder has to be 0. So that condition we can write in this way. G of x, h of x, modulo x to the power n plus 1 should be equal to 0. This is actually equivalent to, some of you might get in the mind right now, if you remember, parity check matrix times generator matrix transpose is equal to 0 for linear codes. These are equivalent conditions. Okay, so there is actually a theory in algebra wherein matrices are represented by polynomials. Okay, so that is a separate theory. We will not go in that direction. We'll just take these basic results. And here is a general way of constructing codes, and which is a very vast research area in coding theory, where that is where actually algebra people came in. That is how to get different cyclic codes. Here is the way. So you take x to the power n plus 1 polynomial, factorize it. factorize it. Okay, you will get several factors. Now, any n minus k degree factor can be taken as generator polynomial, and any k degree factor can be taken as parity check polynomial. I will tell you, it's not so easy. Suppose if I give x to the power 23 plus 1, can you factorize it? And given that you are allowed to choose only binary coefficients 1 or 0, so you will see there are, even right now, papers are coming out. They take up any weird polynomial of any weird degree, even prime degrees. Prime degrees are very, very famous. X to the power 7 plus 1, x to the power 13 plus 1, x to the power 17 plus 1. They have very special, structure. So that is a very deep theory, okay, and that is difficult also. We are not going to do that. We will do very, very simple examples. But just maybe some of you may be interested in taking up their research in this direction, although saturated now and very big shots are doing research in this area. But still, it is very, very interesting. But this is the way to construct it. Now, and there is a great job of choosing good codes. There will be several codes. You can, suppose x to the power 23 plus 1, you can factorize it in various ways, and you can choose any k degree, but you have to choose a good code. Good code will should be which has good error correcting capability. That is one important research area, which is vast, and people have been doing work from last 30-40 years and still doing work in this area. Now I will show you how to construct generator matrix from generator polynomial. I will just show here you the general way, and then we will do the example later. So you have a g of x as generator polynomial. Do one thing. You multiply, so first of all you have g of x, then you multiply x with it, then x square with it, finally x to the power k minus 1 g of x. Okay, and these n tuples correspond to the polynomials. Okay, these n tuple polynomials, they can be used as rows of k by n generator matrix. Okay, so right now you just remember this fact, and later on when we will do one example, it will become very clear. So we can construct, so given g of x, you have to do one thing, multiply x with g of x, then multiply x square with g of x, and then multiply x to the power k minus 1 with g of x, and then take the coefficients and take the coefficients of all of these polynomials and form a matrix of them, and you will get this generator matrix. However, the construction of parity check matrix from parity check polynomial is little bit involved. It needs some attention. So first of all, you have the relationship. The relation is that g of x h of x is equal to x to the power n plus 1. Okay, now if I multiply a of x on the both sides, so I will get a of x plus a of x x to the power n. Now a of x g of x was defined to be code word of x c of x, h of x is equal to a of x plus a of x x to the power n. Now note down that c of x has degree n minus 1, h of x has degree k, so c of x h of x has degree up to n minus k, n plus k minus 1. Okay, on the right hand side you have a of x, its degree is k, so it will contain terms from 0 to k minus 1. Right, it has degree k minus 1, 0 to k minus 1. Then this x to the power n it will contain the terms from n to n plus k minus 1. So there is something missing. See, on left hand side you have all the terms from 0 to the degree n minus k plus 1. On right hand side, a of x contains terms from degree 0 to k minus 1. This term contains degrees from n to n plus k minus 1. So what is missing on right hand side? What are the missing terms? The k degree term, x to the power k, x to the power k plus 1, up to x to the power n minus 1. After that, x to the power n is there, right? So these terms, these powers are missing. They don't appear on the right hand side. Okay. So on left hand side, to make this equation compatible, we will have to set. So we will have to set the coefficients of these degrees in the expansion cxhx equal to 0. And when you will multiply cxhx and you will identify the coefficient, suppose if you write c of x times h of x equals, this is c naught plus c1x plus cn minus 1 xn minus 1 times 1 plus h1 x plus h2x square plus hk minus 1 x to the power k minus 1 plus x to the power k. You multiply them and you find the terms which have degrees x to the power k, x to the power k minus 1, x to the power n minus 1, and put that equal to 0. You will obtain this type of equation: I equal to j to j plus 1 ci h k plus j minus I equal to 0. This is a small assignment for you. Just verify that it comes like this: for 0 less than equal to j less than equal to n minus k minus 1. Okay, this basically is same as ch transpose equal to 0 in linear codes we have done. Hence we have the following important observation. So this relationship, we observe an important thing, that the coefficients of parity check polynomial, so it is not p of x, it is h of x, okay, involved in the polynomial multiplication described above are arranged in reverse order with respect to the coefficients of parity check matrix involved in forming the inner product of vectors ch transpose equal to 0. So this relationship we know. You look at this relationship, you have here I equal to j plus 1, right? And then you have here k plus j minus I. So as I increases, j minus I will decrease. So hence ci gets multiplied reversely with h here, and it is equal to 0. If you compare this with this equation, ch transpose equal to 0, so the equivalent of h transpose is of the reverse order as compared to the coefficients of parity check polynomial h j plus k plus j minus I. Okay, so after this observation suggests us that we should not directly use parity check matrix to get the parity check polynomial to get the parity check matrix. Rather than we should do this thing. How to get the reverse terms of h of x? You just, instead of x, you write x inverse, that is you write 1 over x, then multiply it with x to the power k. So what you do get? X to the power k, then this is 1 plus summation I is equal to 1 to k minus 1 hi, and then there will be here x to the power minus I plus x to the power minus k. Right, now you multiply x to the power k, you will get first term as x to the power k plus summation hi x to the power I, right, plus 1, or not I, sorry, x to the power k minus I plus 1, which I can write as 1 plus okay. Now what should we do? We first have now x to the power k h of x inverse, then write x to the power k plus 1 h of x inverse and x to the power n minus 1 h of x inverse. And these rows of the coefficients of these polynomials can be used to get the parity check matrix. Just hold on, when we will do one example, it will become more and more clear what it means. Now, we can also design the encoder design with the help of generator matrix like this. So we recall there are three steps for generation of a code word from generator matrix polynomial. So here are these three steps. First, you multiply x to the power n minus 1 with m of x, then you divide it by generator polynomial, then you get remainder, and then you add b of x, the remainder, to the x to the power n minus 1 and m of x, you will get the desired code. These three steps can be realized using digital circuits. Okay, see what is done. Each degree, as I told you, suppose you multiply x with something or x square with something, it actually means you are shifting, right? So you will use flip-flops, okay, as those shifting elements. And so what will be the rules? We have here flip-flop. It simply stores a bit, and whenever clock ticks in, it will whatever is at the input of the bit, that is stored, and whatever is inside flip-flop, that comes out of the flip-flop. That is the simple rule of flip-flop. Okay. So the first term, that is of the generator polynomial, okay, is 1. So there will be a connection here. Okay. Then the second term is summation gi x to the power I is equal to 1 to k minus 1. So depending upon whether gi is 1 or 0, so I will write here like this, g1, and then here is the XOR modulo 2 operation. Okay, so this particular thing is equivalent to writing g1 of x. That is what it means. Sorry, is equivalent to writing g1 times x. Similarly, if you put another flip-flop here, and if g2 here, so this becomes equivalent to g2x. Okay, so on so forth. So then you have here g of n minus k minus 1 then we have a gate here, and when you will when the clock will tick and it will shift it, this is equivalent to division operation of x to the power n minus k, m of x and g of x. Okay, so if you go back to digital electronics and see how divisors are designed there, you will get it. If you don't get it, you can simply remember it also. So the output at this point, okay, that will be the parity bits, the remainder b. Okay, and here we are supplying the message bits. So these message bits will be used in this way. So first of all, they will be directly fed here, and these parity bits will be added to the message bits, right? And you will get parity bits here and message bits here, and here you will get the code. So you know what is done. You feed in the message bits. The first bit comes here, gate passes them. The message bits are put in this flip-flop, and depending upon whether G1, G2 is 1 or 0, they will be added up here. And after each clock tick, these message bits will get shifted. New message bit will enter. The overall operation mimics the operation of division. Division of what? X to the power n minus k times m of x divided by g of x. Okay, and you get remainder here, which you then concatenate with the message bits, and you get the code word. Okay, so let's take one example so that it becomes clear. Now a lot of things will become clear here. So I will come back to having cyclic codes. Okay, so having code, I will take here 7-4 code, that is k is 4 and is 7, right? So how to get generator polynomial and other things? So you have to take x to the power 7 plus 1 polynomial and factorize it. I will not trouble you with saying that you should be able to factorize. I will myself give you factors in examination, so you don't worry about this. Okay, so one factor is always 1 plus x, which is not directly of any use. So you can choose any of n minus k degree, that is 7 minus 4 is 3 degree polynomial as generator polynomial, any of these two. Suppose I pick up this one, 1 plus x cubed, so I get g of x is equal to 1 plus x cubed. Now this is your generator polynomial. So what will be the parity check polynomial? The rest of the thing, definitely, that is of degree k. K is here 4. So this is of degree 4, which will be 1 plus x times 1 plus x square plus x cube, right? So this is equal to 1 plus x square plus x to the power 4. This is now your parity check polynomial. Okay. Now suppose we want to encode a message 1001. First we will write message polynomial for it. See, now things will become very easy. Its message polynomial is 1 plus 0 times x plus 0 times x square plus 1 times x cube, which is 1 plus x cube. This is its message polynomial. Now what is the first step in encoding? So first step is you have to multiply x to the power n minus k to m of x, which implies you have to multiply x to the power 7 minus 4 to m of x, which implies you have to multiply x cube to 1 plus x cube, which becomes x cube plus x to the power 6. Nice. Now next step is you have to divide this x cube plus x to the power 6 with g of x. Okay, so it becomes like this. So here is x to the power 6, here is x cube, and here is g of x, x cube plus x plus 1. Simple division you might have done in 9th class, I think, polynomial division. So what will come here is first x cube, this will become x to the power 6 plus x to the power 4 plus x cube. You will get x to the power 4, then plus x. You will get x to the power 4 plus x square plus x. You get x square, sorry. Now degree of remainder is less than degree of the dividend, so hence we cannot reduce further. So we got the parity polynomial as x plus x square. This is your parity polynomial. Now how to form the code word? You have to write parity polynomial plus x to the power n minus k times m of x, which is x plus x square plus x cube plus x6 Now you write the coefficients properly. So the constant term is 0. Then you have x plus x square plus x cube plus 0 times x4 plus 0 times x5 plus x6, right? So this is your C0, C1, C2, C3, C4, C5, C6 coefficients. So the code is 0, 1, 1, 1, 0, 0, 1, right? See, it is systematic. This is your message part. Okay, so we have got the code word. Now I will generate the generator matrix from generator polynomial. Now it is very easy to demonstrate here. So g of x is 1 plus x cube. Then you write x g of x. It is x plus x square plus x4. Then you write x square g of x, which is x square plus x cube plus x5. Then you write x cube g of x, which is x cube plus x to the power 4 plus x to the power 6. So we have to do only these much operations because I will form now the rows. See, I will write here a matrix, or let me write it equivalently. Okay, see, the first term is 1, second term is 1, right? Then x square is missing, so 0. Okay, x cube is there, so 1. X to the power 4 is missing, 0. X to the power 5 is missing, 0. X to the power 6 is missing, 0, right? Second, here the constant term is missing in this, so 0. First degree term is there, 1. Second degree term is there. Cube term is missing. 4th degree term is there. Then 5th degree missing, 6th degree missing. Then in third row, you have x and constant is missing, so constant C0 is missing, C1 is missing, and then x square term is there, x cube term is there, x to the power 4 is missing, 5 is there, 6 is missing. Then finally constant term is missing, first degree term is missing, second degree term is missing, cube term is there, 4th degree term is there, 5th term is missing, and then 6th term is there. So this will become generator matrix. But you might be confused that generator matrix had a structure. The first part was the parity check part, the other was IK. But here you don't see that, okay? You don't see, because you see there are this. So you just have to do some manipulations, right? You can suppose if you add first row to third row, okay? So first row is here, and add third row to this, and then adding the sum of first two rows to fourth rows, those usual matrix manipulations, you will get standard form 1 1 0 0 1 1 1 1 1 1 0 1 1 0 0 0 0 1 0 0 0 1 0 0 0 0 1. Okay, since your exam is of very short length, so I will not give you such problems where you have to convert into systematic form. It takes time, okay, but you should know the procedure. Now, how to compute parity check matrix? For that, you have first parity check matrix. What was that defined to be? Parity check matrix was taken 1 plus x square plus x to the power 4. So what is the way of generating the parity matrix is, first you have to multiply there's a message there. So x to the power k h of x inverse, then x to the power k plus 1 h of x inverse up to x to the power n minus 1 h of x inverse. So now how will we do that? Here k is 4, so x to the power 4 h of x inverse is x to the power 4 1 plus x inverse plus x minus 2 plus x minus 4, which becomes 1 plus x square plus x cube plus x4. Similarly, compute x to the power 5 h of x minus 1, that becomes x plus x cube plus x4 plus x5. Similarly, x6 h of x inverse, so you have to do up to x of n minus 1. N minus 1 here is 6, so this is the last thing we have to compute. This is x square plus x4 plus x5 plus x6. Now do the same thing, form a matrix, right, and write the coefficient of these degrees in row wise. So you will get 1 0 1 1 1 0 0 0 1 0 1 1 1 0 0 0 1 0 1 1 1. Again, this is not a standard form. You will have to do something, add third row to the first row, and we will get 1 0 0 1 0 1 0 1 0 0 1 0, then 0 1 1 1 1 0 1 1 1, which is same as we have done in the linear course. And finally, we had to do the decoding, correct the errors. So we had to calculate the syndrome. Calculate the syndrome. So you recall that you had a code word C, and at receiver you received the right. This is called a syndrome. Now corresponding to syndrome, you have a syndrome polynomial. As r of x is equal to r naught plus r1x plus rn minus 1 x to the power n minus 1. Okay, this is your syndrome polynomial. Now if we divide this syndrome polynomial, by g of x, suppose you get quotient as q of x and finally remainder as s of x, so you can write r of x as quotient times dividend plus remainder, sorry, s of x. Okay, sorry, this is not syndrome polynomial, I am extremely sorry. So this is the received code polynomial, okay, what you received, not syndrome polynomial. So the remainder term s of x, its degree will be definitely n minus k minus 1, because r of x has degree n minus 1, this has degree k, and the remainder will have degree n minus k minus 1. This remainder polynomial is called a syndrome polynomial. Okay, because you will see that when we do the example that its coefficients are made up of n minus k cross 1 syndrome. Yes. Okay. How to realize it in hardware? Again, we will use flip-flops and XOR gates for it. So here are the received bits. And each term, each degree shift is realized by flip-flop, and this will be G1, this will be G2, Gn minus k minus 1, okay. So this so the output of the last state of the flip-flops will be the syndrome. Okay, after shifting all the bits, that will be syndrome. Now if we go back to the example having code, that is more easy. So first of all, I will draw the encoder. So you have, this is your generator polynomial, right? See, there are 3 degree terms, 1, G1, then G2 is 0, and then G3. Okay, so here are your message bits. This is the way to draw the encoder. Here are your message bits. Now start with this point, right, and then put a XOR gate here, and first term, since this corresponds to highest degree term here, right hand side, so this corresponds to x cube term, it is 1, so it will be, link will be there, and then move here directly. This is the first term, and flip-flop determine is the first degree term. Okay, flip-flop, then XOR. Now see, X is available, so G1 is 1, so I will have a link here. It means G1 is 1, right? Then flip-flop. Then there was actually G2 here, but G2 term is not there, that is 0. So it means this link is not here. So there is no need of XOR gate here. Directly second flip-flop. Okay, and then here. Okay, this is how we just see which degree terms have coefficient 1 or 0. Accordingly, join that at the top. And now the output of, oh sorry, I made a mistake here. So this, actually this XOR should be here, and here I should feed the message bits. Okay, and the output here after shifting all the message bits will be parity bits, and the concatenation of parity and message bits will give us code word. Okay, so this is how we can put here a gate. Okay, okay, now I request, because the lecture is already a 1 hour, so now this is the last thing in your digital communication part. Okay, so I request all of you to study the example from the Simon Hacken book, example 2. Okay, go back to that example and then look at it carefully. If you have any doubt in that, you can come back to me. I have given the sufficient theory. Lecture is already 1 hour, so I will now upload it. So this much is for the digital communication course. Okay, any other video which I will upload, that will be explanation of the existing concepts. There will not be any new concept now onwards. So you can watch those videos to further clarify your concepts. Okay, thank you.